Welcome to this explainer. Okay, today we are exploring something absolutely wild. It's a highly speculative but honestly fascinating alternative framework for looking at the massive amounts of data pouring out of the Large Hadron Collider. It's called the Raihan Atomic Model, or RAM for short. It was developed by an independent theoretical physicist, Dr. Ahmed Raihan, with a rather unexpected assist from Grok AI, which kind of proves chatbots are doing a lot more than just writing our emails these days. This model actually challenges our most fundamental assumptions about atomic structure. So we're going to unpack exactly what this model claims, how it entirely reimagines the subatomic world, and how it just might solve some of the biggest, most persistent headaches in modern physics. Okay, let's dive into this. I want you to picture the Large Hadron Collider, the LHC, as the scene of a grand cosmic detective story. When physicists smash protons together at speeds right up near the speed of light, they capture this incredible, mind-boggling data. But they also repeatedly run into a glaring mystery: missing transverse energy. Particles collide, debris scatters everywhere, but when all the math is tallied up at the end, a significant chunk of energy is simply unaccounted for. Where does it go? And for that matter, why haven't we found the bizarre new physics particles we totally expected to see by now? This missing energy is the central mystery we are unraveling today. So here's our roadmap for this explainer. We'll start with those unsolved LHC data mysteries, then we'll dive into the Riemann atomic model itself. After that, we'll look at reinterpreting the Higgs and energy, outline a falsifiable physics prediction, and finally, wrap up by simulating the nuclear sandwich. I promise we're going to break all this dense physics down logically. All right, let's get right to Section 1, Unsolved LHC Data Mysteries. To really appreciate a totally new theoretical framework, we first have to establish the baseline facts, like what is the current scientific consensus actually observing right now? Well, here is what the LHC has definitively documented over the years. Back in 2012, they famously made global headlines by finding the 125 gigaelectron volt Higgs boson. It was a massive triumph. But, as we mentioned, they also found substantial missing transverse energy, often just referred to as MET. Furthermore, despite pushing collisions to massive energies, we're talking 13 to 13.6 TeV, the exotic, beyond standard model particles we expected to see, like supersymmetric partners, just haven't shown up. Meanwhile, the data continues to confirm that the proton isn't some solid point, but a messy, composite swarm of quarks and gluons. Which brings us to Section 2, the Riemann atomic model. Now, what's really interesting about this is how Dr. Riemann tackles those exact mysteries with a really bold assertion. He claims the proton is not a messy swarm at all, but an intricately structured NPN sandwich wall. Just imagine orthogonally oriented layers, meaning they sit at strict right angles to one another. You have a neutron-like layer, a central protonic core, and an anti-neutron-like layer. It's a rigid, highly geometric sandwich. This model is essentially asking us to completely revisualize the most fundamental building blocks of matter. And it gets deeper. Dr. Rehan posits that these layers aren't just, hard physical shells. They are Gaussian surfaces. You can think of them sort of like nested, bubble-like electromagnetic force fields. And they're maintained in this perfect mutual equilibrium by what he calls a net momentum velocity balance. And honestly, the wildest part? This model suggests that this specific nested geometry scales all the way up, from microscopic atoms right up to the massive structures of planets, galaxies, and the cosmos itself. Moving right along to Section 3, Reinterpreting Higgs and Energy. Let's do a quick compare and contrast here. How exactly does this newly proposed framework map onto the exact same LHC data we just talked about? Well, in the standard model, the Higgs is considered an elementary scalar particle. The missing energy is usually blamed on invisible neutrinos or hypothetical dark matter, and the proton is made of quarks. But in the Riemann model, it's totally different. The 125 gigaelectron volt Higgs is reconceptualized not as a new fundamental field, but as a physically detached piece of that nuclear sandwich wall. And the missing energy? That's just the energy required to reconfigure the remaining Gaussian surfaces after the collision happens. Here is a really crucial distinction. When standard physics loses energy in a collision, scientists often have to hypothesize some pretty wild ideas to explain it, like energy leaking into extra dimensions or being carried away by entirely new invisible particles. The Riemann model keeps things elegantly simple. It avoids those theoretical extrapolations entirely and keeps the energy right here in our normal four-dimensional spacetime. The missing energy is just the physical cost of rearranging those nested bubbles after they get smashed apart. It's literally just an internal bookkeeping item. Now for Section 4, a falsifiable physics prediction. Any good speculative theory, no matter how beautiful or elegant it sounds on paper, absolutely must offer testable, concrete predictions to hold up to the scientific method. And RAM does. It predicts something standard physics does not expect at all, a specific off-balance spray of debris, a charge asymmetric multi-jet topology that correlates directly with the direction of the missing transverse energy. Basically, if the proton really is an orthogonal sandwich, smashing it at high energies should produce jets of debris lying in a specific geometric plane, driven entirely by the shattering of those highly oriented neutron and antineutron layers. And this brilliantly illustrates how the geometry of that sandwich wall literally dictates the math of the collision. We're looking at the azimuthal angle difference of the debris jets here. RAM expects a statistically significant preference for jets firing off at values near pi/2, or 90-degree angles. This would create a very specific, sharp, period pi angular correlation in the data, which is completely unlike the even shotgun scatter blast of standard QCD radiation expected from the standard model. On top of that, RAM expects to see a characteristic shoulder, or a secondary peak, in the missing transverse energy spectrum right at the 70 to 110 gigaelectron-volt range. According to the model, this specific number isn't random. It represents the typical energy cost required to physically reconfigure one of those Gaussian walls after a collision. Standard model neutrino missing energy spectra completely lack this feature. And to his credit, Dr. Rehan offers this set of predictions as a clean, ruthless discriminator. He states clearly that if this specific non-zero charge met asymmetry and orthogonal signature are absent in the data, the model is constrained or entirely ruled out in its present qualitative form. This is just excellent, impartial scientific practice. The data is either going to validate this composite geometric picture or it's going to prove it definitively false. Finally, we arrive at Section 5, simulating the nuclear sandwich. So how do physicists actually test this radically different model computationally without breaking the bank? Well, the paper provides a clear blueprint using next-to-leading order QCD corrections. First, you generate the incoming protons. Second, you build that body-fixed nuclear wall sandwich geometry for each. Third, perform the collision and detachment based on geometric overlap. Fourth, you assign the resulting momenta based on those 90-degree orthogonal fragmentation rules we talked about. And fifth, hadronize the residual systems. This custom process can actually be seamlessly interfaced with standard Monte Carlo simulation tools that physicists already use all the time, like Pythia 8, just replacing the standard hard process with RAM's unique detachment. So the crucial point is, we do not need to build a new, multi-billion-dollar collider to test this theory right now. A dedicated analysis using the massive, existing Run 2 and early Run 3 datasets from ATLAS and CMS holds the keys. The data to test these exact equations is already sitting right there on our servers. Looking for that specific 90-degree angular correlation and that energy shoulder is a direct, incredibly low-cost test that the physics community can run today. Which leaves us with a pretty provocative thought to wrap up on. If a low-cost data test on existing LHC data actually confirms these orthogonal fragmentations, what would that reveal about the true hidden geometry of our universe? It's a fascinating reminder of the true nature of scientific inquiry, how just a simple shift in geometric perspective could potentially rewrite our entire understanding of the atomic world. Thank you so much for joining me on this explainer. Keep questioning everything and keep exploring.